All right, so today we're going to talk a little bit about the correspondence between the angular or rotational motion of an object and the tangential velocity of a point on it. And we know that the tangential velocity of a ball on a string, right? So how fast it's going, if I switch colors here for just a second, okay? How fast it's going at that instant, and then of course how fast it's going at that instant. That velocity, which when we talked about centripetal acceleration and uniform circular motion, right, that velocity, whatever this is, stayed the same magnitude, just changed direction. But it doesn't have to be that way, right? If you've ever done this, you've had a ball in a string and you're whirling in a circle, you certainly can make it go slower or make it go faster. And so the tangential velocity, this velocity that we've just been calling, velocity at this point, we're going to add a subscript t to make sure that we understand that it's tangent to the circle, right? So if you're tangent to a curve, right, and so the tangent to the curve would be like that, right? That would be a line that's tangent to that curve, just touches it at one particular point, okay? And that's essentially what we're doing here with our velocity vector, always tangent to the curve. In other words, perpendicular to the radial direction, okay? So hopefully that's clear. Now, how is that tangential velocity related to the angular speed? We know it must be, right? If you're going around that circle more times in a second, then you would expect your tangential velocity to be larger. And you could reason that out in a number of different ways, but right, you have to go around the entire circumference of this circle in X amount of time. Oh no, okay. And to go around the entire circumference of this circle in X amount of time. If you're making that trip in a shorter period of time, then you have a higher tangential velocity. If you're making that trip in a longer period of time, then you would have a lower tangential velocity. Okay, so there's some number of meters that's being covered every second, and your tangential velocity is telling you exactly how much distance that is. As far as connecting the angular velocity to the tangential velocity directly, well, we have a way that we can do that. And we can look at it a couple of different ways, but if we take the definition of angular velocity, right? So remember, this is angular velocity, technically average angular velocity, okay? And we write out its definition, so angular displacement over some period of time, and we replace the angular displacement with this expression, right? So we solve for delta theta, we substitute in what we see here, delta s, the arc length covered in that period of time, divided by the radius of the circle. And then we redistribute the r down to the bottom. Delta s over delta t, okay, that's just going to be the tangential velocity, right? It tells you exactly how long it would take to cover that many meters, okay, in a certain, how quickly you would cover that number of meters, right? So delta s being 5 meters, you cover it in 1 second, then you know that your tangential velocity is 5 meters divided by 1 second, which is 5 meters per second. And so the expression for the connection between angular velocity and tangential velocity is the following, okay? Just omega equals tangential velocity of the ball, in this case on the string, divided by its distance from the axis of rotation, right? So that's the r, distance from axis of rotation. Now, it's also the radius of the circle that the ball on a string is going around, but I wanted to spell it out as distance from the axis of rotation because if you take a different point on the string, like say you have like a little second ball right here, or you just pick a point on the string, well, then you're going to be carving out a smaller little arc length. So even though your angular velocity would be the same, it's still going around the circle the same number of times in a second, the number of meters covered by that red dot is smaller, and so you'd expect a smaller tangential velocity for that object. Okay. Now, and if you consider a change in the tangential velocity, so say you start whirling the ball on a string a little bit faster, then we can divide both sides again by some delta t, and you end up with a relationship between the tangential acceleration and the angular acceleration. Okay? You'll notice that if we just rearrange this a little bit, we end up with something that looks very much like what we've got above, right? So we've got angular quantity equals tangential quantity divided by the distance between the axis of rotation and the point of concern. So the ball and the string in this case, maybe the edge of the tire, or a card and the spokes of a wheel, or something along those lines, okay? So this is the connection between angular and tangential variables, and this is going to be the root of how we connect the rotational motion of, say, a rolling object to how much ground it's actually covering as it rolls along. So let's think about me on that bicycle one more time. And the only crucial additional piece of information that we need is the radius of my wheel, okay? Because if we don't have that, then we can't make a connection between the tangential velocity of the wheel and its edge as it touches the ground and the rotational motion that we know so much about in this problem, all right? And that it comes to a halt over here. Okay? So, question being, okay, how far do I go, right? What's my stopping distance? Because sure, I can count how many times my tire goes around, but I'm really interested in, like, okay, if the truck is right here, okay, is my stopping distance, so how far I'm going from this point to this point, is that going to be small enough so that I don't smash into the truck? Okay, so we need to connect this angular displacement to some distance actually traced out on the ground, and we can do that with this relationship between arc length and angular displacement. So I've already substituted in the numbers here, 1/3 of a meter for the radius of my bicycle tire, 81.7, rounded a bit there, rads for the angular displacement, which gives me that the arc length traced out along the surface of my tire is 27 meters, which is exactly the same amount of linear distance that I'm going to cover along the ground, okay? So from hitting the brakes to stopping, the bike and me cover 27 meters, all right? Now, if you wanted to know, for instance, the velocity of a point on the edge of my wheel as it relates to how quickly the wheel is spinning, well, then again, you can use the tangential velocity equation, which is this, okay? And for this, you would have 0.33 times 30 rads per second, which 1/3, approximately, of 30 is just 10 meters per second, okay? So I'd be moving at 10 meters per second, which is a pretty good clip, though not unreasonable for a bicycle. So we'll leave it there, and when we come back next time, we'll talk a little bit about rolling motion, because one thing that is a little bit tricky here is that I have just implicitly said that the linear distance covered, like if I were to like take a piece of chalk or like a string and wrap it around my tire and unravel it as I went along the ground here, then that string all laid out in a line would be exactly equal to the number of, the distance around and around and around and around, counting up all those circumferences of the circle as I roll along. That is not always true, though, is it? Right? If I slam on the brakes really hard, I might lock up the wheel, in which case my angular velocity is 0, whereas I would still be moving as I skid in a linear way. So there needs to be some sort of formal connection between the sort of distance along the arc, along the edge of the circle, and the distance actually covered as I roll forward. And when we talk about rolling motion, we'll talk a little bit more about the details of that.